Okay, good morning. This is Group 11. We are performing a project on hot electron effects on MOS transistors, and here we are trying to show the change in the parameters when the hot electrons are simulated in the typical NMOS transistor. So, talking about hot electrons are generated by pushing the channel electrons into the oxide, degrading the oxide by storing the electrons inside the traps, which changes the threshold voltage, transconductance, and also the ID versus VGS curve. This project helps us to simulate the hot electron effects, observe the change in parameters by stressing at different times, and observe its changes. We also observe the changes when there is a change in the source and drain doping, along with the different stress times. Now, the principal objective here is to simulate the hot electrons and observe what happens when the hot electrons are injected in the oxide layer. And also we observe the shift in the parameters caused by these hot electrons. And also we observe what happens when there is a change in the doping concentrations in source and drain. We hereby note down the ID versus VGS plots in different stress times from 0.01 to 10,000 seconds. And we expect that there will be a shift in the ID versus VGS, and increase in the threshold voltage, decrease in the transconductance, and increase in the subthreshold slope when subjected to long periods of time.
So the hot carriers are the electrons or holes that gain the high kinetic energy in high field areas of semiconductor devices, such as MOS devices, which can cause device degradation or malfunction when they become trapped in the unintended areas. The term hot carrier effects refers to device degradation or instability caused by these hot carrier injections. So there are basically 4 types of hot carrier injection mechanisms. The first is drain avalanche hot carrier injection, which occurs when drain voltage is greater than the gate voltage. The worst occurs when the drain voltage is twice the gate voltage. And the channel hot electron injection, which occurs when both gate and drain voltage are higher than the source voltage. And then substrate hot electron injection, which occurs when substrate back bias is very positive or very negative. And secondary generated hot electron injection, which is generation of hot carriers through impact ionization of secondary carrier created by the prior impact ionization event in DAHC.
Okay, so basically transconductance is nothing but the measure of sensitivity of the device current to changes in gate voltage. So it is basically defined as derivative of drain current with respect to the gate voltage at any bias point. So hot electron effect depends on transconductance because higher the transconductance, higher the electric field at the drain edge of the channel, which increases the probability of hot electron generation. Coming to the subthreshold slope, it is nothing but the inverse of slope of log of current versus voltage in subthreshold region. So the lower the subthreshold slope, the steeper the IV curve and more sensitive the device is to changes in gate voltage. So hot electron also depends on subthreshold slope because lower the subthreshold slope, the higher the electric field at the drain edge of the channel, which accelerates electrons and increases the probability of hot electron generation. So to summarize this, both subthreshold slope and transconductance have an impact on the probability of hot electron generation in a semiconductor device.
Threshold voltage is the amount of gate voltage that is required to start the flow of current between the source and drain terminals. This voltage level can be affected by hot electron effect. In a typical NMOS transistor, threshold voltage is affected by hot electron effect when the high electric field accelerates the electrons trapped in the channel. And this relationship is represented by an equation. This equation suggests that the change in threshold voltage due to hot electron stress is proportional to the amount of charge trapped in the gate oxide, and it is inversely proportional to the temperature. And as you can see from the slide, this equation for the change in threshold voltage is given, and from this equation we can see that the threshold voltage is directly proportional to Q, which is the amount of charge that is trapped in the gate oxide, and is inversely proportional to the temperature. Now coming to the relationship between a drain current and gate source voltage, and the effect that hot electron stress has on this relationship. We know that the relationship between ID and VGS can be affected by hot electron stress, and hot electron stress it causes the generation of traps in the gate oxide, which alters the threshold voltage of the device. And taking into consideration of the hot electron stress, which of the effect the hot electron stress has on threshold voltage, we are given an equation for ID and VGS, which is modified. And thus, from this equation, we can see that it suggests the drain current is dependent on the gate to source voltage, the threshold voltage, and saturation voltage. And it also takes into consideration the effect hot electron stress has on threshold voltage. And as we saw previously, the threshold voltage, it is proportional to the charge trapped in the gate oxide, and it is inversely proportional to the temperature. And from the graphs on the side, we can also see the change in the relationship between the ID and VGS curves before and after hot electron effect.
Okay, talking about the technical approach, we use Silvaco, a TCAD tool, to simulate this whole experiment. First, we constructed an NMOS using the Atlas commands, and the gate and substrate were doped at 10^16, and the source and drain are doped at 10^20. We used a mobility model, and also the recombination models, and we used a high electric field from 0.5 volts to 6 volts. Which is a very high electric field for a typical very small NMOS, very small channel NMOS. So here we simulate the hot electrons by using something called as HEI, which is a model, and also we use a degradation model, which simulates the oxide, which simulates the traps inside the oxide layer. So after constructing this whole thing, we tend to create the ID versus VGS curves without any stress, without any degradation model. And we note down the values in the curves. And after giving a degradation model for a specific amount of time intervals, we took the time intervals as 0.01, 0.1, 1, and 1000. And for each and every time interval, we get all the parameter values and the ID versus VGS curves. And we also change the doping concentrations in the source and drain, and we observe the same. And we repeat the same using these time intervals.
So the literature review on the hot electrons and the occurrences was collected by me, and the comparative study on the relationship between various parameters and hot electron stress is completed by Kaushik and Anirudh. Construction of Silvaco code and simulation of ID versus VGS curves at different stress times and doping concentrations is completed by Pawan. And Kaushik and Anirudh are yet to extract the transconductance and the threshold voltage values from the ID versus VGS curves. In the next step, I would be calculating the subthreshold slope from the simulated data. In the final step, the project report will be done by all the team members.
Coming to the progress of the project, the literature survey is completed and the code construction in Silvaco is also completed. We have simulated some of the ID versus VGS graphs for various stress times, as my friend Pawan explained, by varying different doping concentrations. And below are some results. And if you see this, we have found the subthreshold and transconductance values for a doping concentration of 10^20 per centimeter cube. So these are some of the results which we have found till now.
Now coming to the remaining work that we still have, and as we had previously mentioned in the previous slide, the extracting the transconducting threshold voltage and subthreshold slopes for the different doping concentration at various stress times, that is still remaining, and still do have to complete the report. And some of the challenges that we have faced while doing this project, we noticed that Silvaco, it has many models and methods for generating the various simulation environments, and finding out the model that we require for our project has been a challenge. And at the same time, by the way, increasing the doping concentration or increasing the trap density in the cross section, it has led to an increase in the computation power, which obviously leads to more time it takes to get the data, and sometimes the project also halts in the middle of the execution, and that has been a challenge.